Doctori, tutto a post. So welcome back to a new video regarding Sane C++ libraries. So what is Sane C++ libraries? Sane C++ libraries is a set of C++ platform abstraction libraries for macOS, Windows, and Linux with the following principles. It has very fast compile times, it's bloat free, it uses or try to use simple and readable code, and it's easy to integrate. You just add a single file to your project and you're done. You don't need to fiddle with any build system. It doesn't use the C++ standard library. It doesn't use exception or RTTI. And as said, it has no third-party dependencies. So what is the topic for today? Topic for today, I will not be coding today. I will be mainly showing some internal details regarding the async library, which is one of the libraries inside Sane C++ libraries. And I'm doing that because I just recently have been refactoring it quite deeply, and I think I reached the point where many concepts are more clear now, and I feel like I would like to express how things are working so that others can understand, I don't know, contribute something, or just learn how and see how I implemented a few things. So before diving into how this is implemented, let's take a look at how it's meant to be used. So these are the unit tests, which is a good way to see and to check how the API is meant to be used. They are a little bit, how can I describe this? When reading this code, you will see a lot of expectations because that's what tests are doing. They are doing stuff. They expect that something happens and so on. So maybe they're not the most readable thing, but I'll try to. One thing you can do is just remove all of the expectations, for example, and this immediately becomes a lot easier to understand. So you have an event loop, which is a queue of asynchronous operations. So before even saying that, so what is this library even doing? This library allows you to do any kind of IO operation in asynchronous mode, which means that this operation will not be done like serially in the thread where you are calling this operation, where you're placing this operation, which could be, I don't know, file read or reading from a socket, but it will be done by the operating system, so without blocking your code, or eventually in a thread pool, which is not currently implemented, but it will be in some future release. Um, so how does an event loop work? What libraries can you see around doing similar things? If you come from the C world, you can see the libuvu library that is powering Node.js, for example. But there is Boost Asio for C++ people, and this is the Sane C++ take on this topic, where we just try to do something simple but at the same time powerful. This library supports already Windows, macOS, and Linux. I'm planning also to expand the Linux support, which is currently using the ep.10 API to use the IO uring API. But for now, this is already working on multiple platforms. So how does the abstraction work? You create an event loop, which is, as I was trying to say earlier, it's it's a queue of asynchronous operations, and in this queue of asynchronous operations, you just add, a bunch of asynchronous operations. But which are operations do you start? So every operation has a start method, but you don't know when they will be ready. So you just add them to the event loop, and then you block on the event loop, and when one operation is finished, its callback will be called. So that's the pattern that you will see used everywhere. This library does not allocate any memory. It's completely free of allocations. So the only objects that provide states are these async objects, and they are, as you will see, they are linked in a linked list. So There is you can basically handle them yourself. So how you want to allocate, it's up to the user, as long as this object is valid and its address is valid, as long as its callback is fully executed. So that being said, what type of objects do we have? Let's see. What type of operation does the library support? The library supports ability to set a timeout. So just, a callback that will get executed after some seconds or milliseconds. There's a WakeUp object, which is an asynchronous operations that allows you to wake up the event loop. What does it mean, wake up? That when we call one of these, run or run once methods on the event loop, if there's no event, will be, sleeping on the first event that becomes ready or available, or that gets completed, to be more precise. So until that happens, the event loop is just, sleeping, and this is how you can wake up the event loop from, for example, a secondary thread. So you have a secondary thread that is doing stuff. You can use the wake up async operation to execute basically a callback into the wanted event loop. We have an object to check for process exit. So when a process is executed, you typically want to monitor when it's finished, like it's Posix child signal, or the analogous on other platforms. This is how you get that type of notification that a process is actually finished. So that allows you to, for example, spawn many processes, like when you are compiling, and spawn them in parallel, and then wait for all of them to be finished. That's actually one of the very easy things to do with the library. Then there is also sort of socket operations, where you can accept a connection. So when you're listening, you have a TCP or potentially UDP listening server. You can accept a new connection, or you can connect to a destination. You can send data, so bytes on the TCP stream. You can receive data. You can close the socket. So these are pretty self-explanatory. So every time you add one of these operations, they will not block your loop, and you can add as many as you want. So you can create 50 connections, 100 connections, 1,000 connections, and wait for them to receive data all at once without and they will just happen concurrently. We have the analogous of this send, receive, and close for file operations. So for operations operating on disk, or even on pipes, actually. And then we have this file poll, which I will probably rename. So maybe sometime from now, this will not be called file poll, will be called just poll, or something similar, that allows you to monitor any OS handle. This is useful because many OS APIs, like even for example, the Linux API to monitor files changed in a folder, is meant to be monitored with a poll type of mechanism, which is just like monitoring a file when something, like it's like a virtual file that is used to deliver events at the end of the day. And so these are the operations supported so far. Maybe I will be expanding this to some other operations, but I think they are already quite good so far. So let's see how this is going to be used in the examples very quickly. So the loop, how does the loop work? You create an event loop. That's how you create an event loop. You declare as many timeouts as you want. I declare 2 here. You fill a callback that will be executed when the timer is expired. So okay, when the timer is expired, I mean, this test is doing this, checking of how many times it gets called. You have to start the timer. So the timer will be the timeout. Sorry, it's also called timer in other abstractions. So maybe sometimes I will call it timer. So this timeout will be fulfilled after 1 millisecond. This second timeout will be fulfilled in 100 milliseconds from now, of course. So we enter the event loop, and so this will block for as much time as this is meant to be executing. So let's try to see. Maybe let me modify this one. So let's do SC test. Yeah, I will just run the run async test first and return 0. Yeah, this is of course complaining. Let's do it like this just to, okay. Of course, this is also complaining about missing return values. So just for the sake of explaining, I'll be removing all of these expectations. So let's just define, yeah, there is a macro. I think it's called SCDZ, warning. Yeah, compile warning push unused result. So this is actually disabling the unused result, and then we pop this. Okay. So, well, of course we don't need this because these are now just equality. Unused parameter okay. So let's try to run this. Let's add, I don't know, report dot print console print timeout 1, and let's do the same with timeout 2, and let's do a print here like before event loop run, and this is after. Let's see what we are getting. Oh, of course I forgot. Maybe I should do a print line. Print line. Okay, so we have before event loop run, we have the first timeout, we have after event loop run, and we have the timeout. So why does this happen? This method that I called is called run once. It's a method that there are three ways of running an event loop. One is run, which just runs until there is no more async operation. There is one run once, which blocks until there is forward progress. So like an actual async operation as finished. And then there is run no wait, which will just like peak, will try to run any async operation that is ready to be for it to have its callback called, but it will not be blocking. So let's see if this is changing now if I increment the timeouts. Let's make this I don't know, 3 seconds, and this one 2 seconds. So this timeout 2 now will be executing before the timeout 1, as you can see, of course. And you see that we have been, while we were in this 2 seconds, if I now if I pause the execution, let's do debug pause, we are in this run once. Actually, I paused it when it was already going in the second one, but as you see, there is always a blocking call, which depends on the operating system. It's key event on macOS, it's epoll on Linux, and it will be IOU ring on the, actually it's a little bit different, the IOU ring, but you get the concept. There is a blocking call that waits for events to be either ready or for an async operation to be completed. When this happens, the CPU utilization is 0. So the application or that thread is sleeping, waiting for these new events. So now that we understand how this is working, let's see the other operations. So maybe I can do the same treatment here. Well, maybe we don't need it. Okay. So this is the wake up. So what's the test doing? The test is creating an event loop. It's creating, this is a lambda that runs on a different thread. So there's a new thread being created and started. And inside this thread, we are waking up the event loop, calling this wake up from external thread, which is kind of, self-explanatory. So the main thread will be blocking here and it will be unblocked by this call. There are other tests doing the same, but you get what this is doing. The cool thing about the wake up object is that you can specify a callback, and this callback will be executed in the context of the event loop. So in the same thread that is running the run once in this case, or the run of the event loop. So this is useful because you may have a secondary thread, like, I don't know, it could be this one or this one, that is producing stuff, like, I don't know, is loading something, it's doing something on a thread on background, and then this system wants to somehow add the results to I don't know, a UI, for example. And if the event loop is somehow synced with the UI, so it's running in the same thread, or let's say it's dispatching the callbacks on the same thread where the UI, where it's safe to touch things regarding to UI, then you can just fill the callback and call the wake up from your secondary thread, and you will have no threading issues at all, because your callback code will be executed in the context of the main thread. And there is actually a variation of this wake up that has this, it's called the event object, that you can use it to wait so that you can continue execution in your background thread only when the callback that is executed in the main thread of the event loop, it's fully executed. So this is pretty cool. For people that comes from libuvu background, this is kind of like the uvu async object. Now, there is another test here where I am creating some processes. Actually, well, the test is creating processes that fail, and it's trying to do things that a good test should be doing. But the concept is, again, we have an async operation that we fill with a callback, and that we start to listen for in this case, a process handle, which is a handle we get when launching a process. So we use the process library in this case, but you are free to use just, even to use your system APIs and not use the process libraries, because the many libraries in Sane C++ libraries are not meant to be, you're not like mandated to use them together. It's not mandatory. You can just, as long as you're able to get a handle to a process, which is a PID on Linux, and it's a handle on Windows, you can just use it with the library. So it's not forcing in any way how you should be launching your process. And it gives you just a callback to say, okay, this process has finished, and you can check its exit status, and to check what's the return code for that child process. So that's the process object. And socket accept, I mean, now there is all of the family of socket operation. This is probably way too complicated task to explain right now. I mean, you could dig into it, but it's literally accepting a socket, which means it's spawning TCP server on a port. There is a thread that tries to connect to that, and this is and we are creating a SocketXXX operation, which is an operation that has a callback, and this callback is called when a new connection, a new client arrives on that listening socket. So very simple, and it gives you an already created socket handle, so you can use it. In this case, I'm wrapping this created socket with with socket client library, which is another object coming from the socket library in Sane C++ libraries, but you can use anything you want. Again, this is giving you back the raw socket descriptor. So your socket descriptor is just, I mean, it's a unique handle, which is just, on Linux, it will be the file descriptor of the socket. Socket connect is doing the reverse, so you just connect to, hey, I have an IP address, I want to connect to that IP address. And if you see this is how the start looks like for an async connect, and we can see the test. Socket connect creates the event loop. It's parsing the address from port. Yeah, there's one more thing you need to do when working with sockets in the event loop. You need to either create the socket using the event loop, or if you create it externally, you have to kind of register it with the event loop, or because there are some specific APIs on Windows that require somehow the socket to be associated with the event loop. So there is this associate externally created TCP socket, which you can use if your socket comes from another source, or you can just create a async TCP socket if you are staying within the what's provided by Sane C++ libraries, which kind of makes sense if you try to use the library. But if you are trying to integrate this somewhere else where this is not possible, then this is your you have basically all the options. And there is send and receive, which is read and write data, and again they are asynchronous operations. They operate on spans, so we are never owning the data. So it's entirely up to the caller to make sure that this data is valid and available for the entire duration of the async operation. Also when receiving data, you will have to provide a buffer, and that buffer will be filled with whatever available data comes from the socket. So again, this is all manual. It's kind of a lower level interface. Is it convenient to use? Well, it kind of depends. Probably one could be building a slightly more higher level API here that is handling buffers, and so that you don't have to worry about it. Even if I have some ideas to expose this kind of functionality already optionally inside the API, so it will still be by default non-allocating. But if you are okay with just a managed set of buffers that are maybe pre-allocated, then the library can handle them for you. And I think this would be mapping pretty nicely also with some IOU ring API, so that could provide also some capability for to do fancy things like reading file to socket and writing it to socket without going through user space. Probably, I've not investigated it in deeply, but I think it should be possible. Well, there are this boring like socket close, which again you want to be closing the socket, and that may be triggering some networking delays, waiting for things to be closed. You can run this as an async operation, and you have file read and write and file close, which maybe the only difference is that you can specify in the file read and write, you can specify the offset where you want things to be read. So in the start, let's see, async file read, there is an offset parameter that you can actually, this should be commanded to do command, where you can say, okay, I want to read this file at this offset. Of course, you have to be careful because this can be used also for pipes. So using a non-zero offset for a pipe, I think it's going to fail. But all the API is fully no discard and returning results. So if you do something wrong, you will get an error for sure. It will not just go unnoticed. So this is the functionality of the library. This test is definitely going to be something I think I should be expanding, or we should be expanding, hopefully. But it's okay for now. So let's see a little bit of the internals. Internals. So the async library, even just file structure is just this async h and cpp file. Maybe I will split this into multiple headers because it's getting kind of big, but I think that's all right for now. And then there are internal implementation file for each backend. So in the CPP file there's like the common part between all platforms, and here you have the specific platform platform specific code. It's kind of heavily commented. I mean, you can always do add more commands, but I guess that's a start. So first thing I would like to show is that this async request object is, the parent of every async request object. It has this intrusive linked list pointers that allows us to chain them into, and have them ordered without needing to keep or own any vector of async requests. You can retrieve the event loop. So, I mean, we can see what does it have. It has a pointer to an event loop. It has, a debug name, which is useful when you're trying to, at least it was useful for me to debug like some really weird situations with bugs. And more importantly, it has a state and a type. So what is the type? Type is, any of the async operations type. So very, that's just a list of supported operations that can be expanded. And what about the state? Let's see the state. So the state is very important for the internals of the library. When you create an async operation, the operation is going to be marked as free. And this means that it's an handle you can use with async start. So just you can fill it and you can start it. In the exact moment you start on a handle, you will get the async object will go in the setup state. The setup state, it means it will receive a setup, which is like the one-time setup. Then once you set up something, it will go into actually it will, sorry, I got it wrong. After you start it, it will go in, no, I got it right. It goes in the setup mode, yes. After the setup, it goes into the active. So the setup is the one-time setup, and the active is the activation that gets done every time an async operation is fulfilled and you want to reactivate it. So for example, if you have a socket accept, which accepts socket, you can accept many sockets from a listening server. So you will do a first one-time setup, then activate, then you will get a socket. And if you choose to reactivate that request, then it will get again in active state. Before doing that, it will go in the submitting state because the async operation, to become active, it needs to be submitted to the event loop. Teardown is the opposite of setup, so you will see it in teardown mode when there is a need to basically run some code to unregister what was done by the one-time setup. And the canceling mode is what you will be getting when you cancel an in-flight async operation. So an operation that is active, and you say there is a cancel async, actually it's called stop operation, it will go in the canceling mode, and it will get specific code run for each operation that is, let's say, it's removing the active operation from the queue. So let's try to see, I mean, this looks very abstract. Let's try to see like some real operation. So this is the Posix backend. So for timeouts, we are doing, so each operation on the backend has this this format. And maybe to understand it better, let's see the the M script and backend, which is kind of just like a skeleton for now. So all the phases that I have described associated here with the state are basically also here. So an async operation lifetime will be, you know, you start it, calling it, you know, every async operation as a start. Again, you will see this start everywhere in every async operation. When you start it, it goes in the submission queue. And I mean, I can even show you with this queue submission. This is getting loop queue submission. It's going in state setup, and it's going to be queued into the submission queue, which is just this linked list. Then when in any of the tests we are doing this run once type of methods, then we get to the run step, and the run step is looping through all of the submission and it's staging them. What does stage mean? Stage means if they are in setup mode, they will get their setup called, they will go in submitting mode, and then they will be activated, which is what I hope I said earlier. So we get a setup and we get an activate. So in the very first, you know, run. What happens after the activate? After the activate, the async operation needs to be synced with the kernel. Not all of them needs to do that, but in the abstraction, they do. So the sync with kernel gets called. It's called sync with kernel, not send or poll, because on some APIs you are doing you are bot sending the async operations, and you are reading the results. For example, this is what happens on the K-event macOS API, or the BSD. I think it's a BSD API. So this is doing setup, it's doing activate, then you go in the sync with kernel. We can see this is being done in the async CPP. Sync with kernel. So you end up here because you exit stage submissions. Of course, if you have active handles, you will get synced with kernel. After sync with kernel, what does happen? Let's see, what does sync with kernel do? It's doing the kernel specific APIs, but then we run completions, which means any async operation. So this is a blocking call again, and this can only be unblocked if something happens. Any of the async operation gets fulfilled. So for the ones that get fulfilled, we will execute the completion. And then there is this manual completion, which is something specific. I don't want to go in the detail for now, but it's a mechanism to handle in the same way async operations that do not necessarily get to a completion state by a kernel operation. So for the timeout, for example, we are just adding them to this other list because we just need to track them in this back end in order to find the earliest timer and call the key event such that the earliest timer will time out this call. This is how timers are implemented on almost not every, in most APIs. I've seen it. There are timer specific objects, but when you start to have many timers, having all of them tracked as a kernel object is not probably going to be a good idea. So you always want to keep some sort of user space, data structure, just loop. Maybe it's an ordered set of timers, find the earliest timer and just either set the timeout to it or add that very single timer to the kernel object in order to be noticed about its timeout. So after the setup, after the activate, after the sync with kernel, we validate the event. So we get this event object. In this case, it's an integer, but on different backends are very specific types of objects. It's like k event object in k event API, and it's an epoll event object on epoll, and on Windows it's I don't even remember. Is it like the overlapped? Let's see. Overlapped entry. Yeah. So they all have all of these analogous objects. So this is really cool because it has really been an exercise in trying to align all of these APIs, which are kind of different, especially the Windows one, into a common ground. So let's see another operation. For example, SocketXXX. This is a slightly more complex operation. For example, on Posix, which uses epoll or key event, we are either adding or setting an event watcher. So the setup again, it's the function that gets called only first time. So we take this async handle and we get which we ask to be informed about any read operations happening on it. This is how you're supposed to get notified about an accept operation on these APIs. These are all documented on their man pages for each single API. And when the kernel operation returns notification for it, we run the complete. After the validate, we run the complete operations associated with this very specific async op. So in this case, I will just get the handle. So one of my results is, let's see, async handle. So we get server socket. So basically this is the operation telling us that it's now there is a ready client that we can accept. So I'm using the socket library, socket server, to just accept this connection, which was marked as a non-blocking accept. So, but we know now that this accept will succeed synchronously because we have been told by the kernel that there is a socket that is waiting just to be accepted. And we can see that this is, for example, quite a little bit more complicated, I think, on Windows. I can't remember if it was the accept or the connect. Let's see. Yeah, so on Windows, it's different. We don't have like a setup because Windows doesn't work like this Posix APIs. This Posix APIs, they work on like readability. So they say this socket is ready for you to accept. So now please do the accept. So you get notified about, okay, this is ready. And then you do your operation, which is the accept. On Windows, this is the opposite. You connect with, in this case, you accept. So you initiate and accept, but this fails with an error actually that is called WSAIO pending. And this is fine, which means this is an error that says, yeah, I will be fulfilling this request, not immediately, but at some point, yeah. So you have to wait for it. So we in the activate, we initiate this connection. Actually, in the Windows API, we also have to create the socket for it. So the destination socket that we will be accepting. And when we get notification from the kernel API that we have some new client, socket client that is connected, we have to run some additional code in order to use this new socket that we got. We have to do this accept context and so on. This looks like black magic. It's all documented in MSDN in this case, so it's non-intuitive to do, but that's the coolness of a project like this, because you get so many details already solved for you. Now, so you will see this pattern to repeat it for every operation. So every operation may or may not define some of the steps. So these are like all the possible steps that an async operation can take. All the, let's say, these are like, if we see this as a state machine, these are the methods that are allowing you to move from one state to the other. So when you move from setup to activate, you get the setup called. When you move from activate, so from the setup state to active, the activate will be called, and so on. Not every async operation will need to redefine all of them, and as you can see, this is exactly what happens on the different async operations. So connect is the redefining the activate and the complete, but there is no cancel, for example, because actually there is no cancel. This is probably something we would like to do. Yeah. But like the file write is doing the activate, is doing the complete. File close is doing this, just the setup, because there is no way to do like an async close on Windows that I'm aware of, and so on. So in some cases, like the Posix ones, for example, the file operations on one API, on the key event API, they look like they happen as async operations, but they are synchronous. But the key event API is just fine. It's just signaling them to you like, yes, they are ready. And so you think you are doing async file IO, but you are not. While on the where's the file read? Yes, on the EPOL API, that's even worse, because on regular files, they fail. This API fails, so you have to know it. So you manually do the read operation, which is what I'm doing here in the activate execute file read. It's literally executing a read. But at this point, I don't have any kernel mechanism to tell me when, for this entire abstraction to get my completion callback scheduled for to be called. So that's where the schedule manual completion comes into place. So in cases like this where I'm kinda faking the ability to run this as an async operation, I will run it as a synchronous operation and schedule the manual completion. And you may be asking, why should I be using this complicated async API with you still running things synchronously? Well, that's an abstraction. At some point, these operations will be run on a thread pool. I've not done yet, but once I add a thread pool, this will work completely asynchronously, and you will not, user will not see a change in the API. It will just work as is. Plus, on some APIs like the IOU ring, doing asynchronous file reads is actually possible. with the API itself. So this will map one-to-one with IOU ring. File operations. So as I said again, file operations cannot be asynchronous with these APIs unless you do direct IO, which you don't really want to be doing it unless you are, I don't know, a database or something like that. For regular buffered IO, this is not going to work for you. And in many cases, you with buffered IO, synchronous read and writes, especially with SSDs, may not be that bad. So I guess even offloading those read and writes to thread pool can be done on a per request basis. So the user can decide, yeah, I would like this operation. I foresee these operations to be running with a lot of data, so maybe it's better if you run this on a thread pool. So I will give you a flag in the start when you do a file read to say, yes, this should be really asynchronous, not, just, not asynchronous. Or you can try, if you have like a IO heavy operation, you can say, yeah, I will be, changing the thread to be fully asynchronous or not. It will be probably done more in the form of a hint rather than an actual, execute this on a thread pool, because on some APIs like IOU ring, I cannot control that, I guess. So yeah, that's it. So I think this is kind of going till the end of what I wanted to say in the video. So please go and check out all of the asynchronous operations. If you have questions about, why something is being done, please make sure to uh, write it into the comments, or even on our Discord. And but yeah, or if you find any flaw in the entire state machine handling, which is being done in the CPP file, which is moving all of the async operations between a state and the other state, then it's yeah, let me know, and with an MR or just a message, or pull request. Sorry, merge request is a terminology for another system that is not GitHub. And yeah, I think this could really be enough for today. So what I'm going to do now in the very next video is to implement another backend for Linux using IOU ring, and hopefully this entire abstraction will still be working fine. I think so, because I have been modifying this exactly to map properly with IOU ring, and the entire API is based on completion. It asks for buffer beforehand, exactly for the reason of mapping to IOU ring. So you can see this entire library as trying to map um, other APIs that are not like IOU ring, like K event and ep.10, and make them look more like IOU ring. So that being said, yeah, go and check out the project homepage and download and clone the repo. Try to run things, try to run even the async tests with enable log one, so you can see all of the steps that are being done. So for example, if I run this with that flag on, you will see that there is a pretty nice log of all of the asynchronous operations, how they get activated, how they get set up, they get to complete, they get to tear down, and they get canceled, or so on. So play with the API. Make sure to subscribe, make sure to download and clone the GitHub repo, make sure to join the Discord that is in the link below. And what else can I do? Have fun with Sane C Libraries. See you next time. Bye.